Stu, and introduce the next speaker. It's Bert Schellekens about discrete symmetries. Orientifolds.
Okay, well, let me thank first of all the organizers for both my invitation to the workshop and to this conference. It was really a great time. It went by very quickly. So I'm going to talk about this paper, which was written in collaboration with these two famous best-selling authors here. Okay, so you can. I need the mic. But okay, the mic for that, I think it's working. So, first some general remarks about discrete symmetries. Of course, you hear a lot about them in meetings like this because they're important in building beyond the standard model. The most famous one being R parity, and maybe you need also for these operators in the MSSM. On the other hand, discrete symmetries can be a nuisance. They can kill your favorite model, as Angel showed very convincingly yesterday. They may forbid couplings that you need, and it's better to know about that as soon as possible because you can save yourself a lot of time if certain operators are completely forbidden. So it's interesting that they are used in many beyond the standard model ideas, and it's also interesting that the standard model itself doesn't really seem to need them. And then you can ask the natural question, how generic are these things then in the landscape? If the landscape has difficulties, if the landscape doesn't like them, then this becomes in some sense also less natural. I will not have very much to say about that, but I'll say very little bit. Then there is of course the famous fork theorem in quantum gravity against the existence of discrete symmetries, but that's completely irrelevant for what I'm doing because I'm going to make use of Gates discrete symmetries, which are basically obtained by embedding a Zn in a U1, and that's certainly always possible, and it was already discussed a very long time ago. Okay, so an obvious way to get abelian discrete symmetries is by embedding them into a U1, and an obvious source for a large number of U1s are orientifolds, because every complex brane comes with a U1. These U1s are either anomalous, in which case they become massive, or if they're not anomalous, then two things can happen. Either they stay massless, which you need for the Y boson of the standard model, of course, or they also get a mass from basically six-dimensional anomalies. And what we need to determine is how often it happens that one of these U1s is not completely broken, but is broken to a discrete abelian symmetry. So for that one can examine the axion couplings, which will look roughly like this. Bm is the axion field. In the kind of models I'm going to look at, we typically have in the order of 10 to hundreds of axions. This is the gauge field strength. Na is the multiplicity of the stack, the Chern-Patten multiplicity, and V is some coupling coefficient. Now we're going to compute these in conformal field theory, and then these coupling coefficients are going to be differences between boundary coefficients. It's a coupling of boundary A to the bulk mode M, usually called an Ishibashi state in this context, and it's this particular differences, which of course vanishes for any real brane if A is equal to AC, because then you don't have a U1. So now let's consider a linear combination of the U1s, something like this. And it's obvious, that's not the hard part, that this will remain massless if all of these quantities vanish for any M. But now what's the condition for a remaining Zm symmetry? How can we detect that? Well, you might guess that maybe it's something like this becomes not zero, but zero modulo some integer, but that's a hard condition to impose because these are real numbers, so you don't know immediately what to do. Nevertheless, that intuition is in some sense correct, and let's first see how you can make it a bit more precise. So I'm now going to repeat an argument that Angel already gave yesterday, but I'm going to repeat it in a slightly different form, which is more useful for my talk. We're going to use instantons. So it's well known that if you have a brane stack U1, which is broken by axions, then the perturbative symmetries stay as perturbative symmetries, they remain valid.
But there can be instantons that break them. And these instantons can correspond to one of the gauge branes, or they can be on a brane by themselves, in which case they are called exotic or stringy instantons. And there has been a lot of work about it the last years, starting with these papers. So if there is a Z-N symmetry, it implies that instantons can only violate this symmetry by, not by one unit, but by n units. So if you are able to find the right normalization of your fields, in particular if you can normalize your axions in this way, so we go to the dual basis where we describe the B menus in terms of axions. If they're normalized like this, then the axion looks like this. It has this gauge transformation here. And then we know that an instanton amplitude, a single instanton amplitude, changes by this phase. Now, that means that if you want to build an invariant, you have to insert an operator which precisely produces this violation of the charge. And you have a discrete symmetry if that violation of the charge can only be a multiple of n. So now we're getting the condition that I already announced. This is what you would have to impose, but we still didn't make any progress because these are still real numbers, except now it's slightly better motivated why it should be like this. So if all these numbers are multiples of n, then no instantons can exist violating this symmetry, which suggests that there is a discrete symmetry. So, as I said, these numbers are complex numbers. So let me repeat this point again. This condition is clear in any setting. This is the vanishing, the generation of a mass for the U1. This condition is not completely clear in the general setting, but in this particular setting, namely geometrically in type 2 on Calabi-Yau, this can be analyzed. There you can find the basis where these things are indeed integers, and then you can write down this condition, and this was done last year in this paper, which is the basis for what I'm talking about now. Okay. So now I have to tell you something about the other word discrete in the title, the discrete orientifolds, which is the class of theories where we're going to investigate this. So to build a so-called discrete orientifold, you start with a rational conformal field theory with central charge 9 and NS2 supersymmetry on the world sheet. You can define that on the torus, and then you construct cross-cap and boundary coefficients that allow you to write that theory on surfaces with boundaries and cross-caps, such as the annulus, the Klein-Buttel, and the Möbius amplitude. And those amplitudes you can compute them exactly. In fact, in these theories, you can expand them into integers if you have all that data available. And this is a program that was started a long time ago, mainly by these people. Now, this idea of using n=2 building blocks was initiated by Gepner in 1987 for heterotic strings, and at that time many people expected that this field would quickly expand into huge numbers of possibilities. Well, that hasn't really happened. There are only very few such building blocks that we can use in practice, namely the original minimal models, which are still around, and recently we added one possibility. It took a lot of work to get that completely under control in the way we needed to control it, and that is the permutation of two of these. If two factors are identical, you can make a permutation orbifold, and that idea was already considered in the 80s, but to get all the data we need for building orientifolds, we needed to do a lot of work. This was done with my student Michele Maio. However, we will not use that. We will only use the original Gepner models here. Now, the first steps towards realistic spectra with these models started in 2003 with these authors, and then a year later we managed to find lots and lots of chiral MSSM spectra, which means if you look only at the chiral states, the spectrum is exactly the MSSM. And then of course there are the usual other things, vector-like things and singlets and moduli. Okay, so these models, although the geometric interpretation is still not entirely clear, probably can be thought of as discrete points in the open and closed moduli space. And in this context, one can do anything essentially that one can do also in the geometric case. You can do tadpole cancellation, introduce hidden sectors, you can do axion vector boson mixing, You can check absence of global anomalies. You can consider instantons, as we've done in several papers. And now we would, it would be embarrassing if in this context we wouldn't be able to discuss discrete symmetries as well. And that's therefore the goal of this talk. I should point out that there are two times discrete in the title. That was just to make it sound nice, but they have basically nothing to do with each other. So don't get confused by that. So now we have to investigate these boundary coefficients R to get some integrality condition out. So we're going to use a formalism that during the years roughly 1990 to 2000 we developed with Fuchs and Heissohn and Zweigert and Walcher and some other people as well, which allows us to compute exact string spectra for a very large number of these orientifolds models. In fact, the total number of orientifolds that we can use is about 30,000 for 5,000 modular invariant partition functions. And the interesting MSSM-like models we found are kind of spread over this entire set. Now the geometric intuition that I just mentioned suggests that we should try to find some kind of integral basis for the boundary coefficients that we need. Something similar was already done by Brunner et al. In a paper in 2004, and they considered the quintic Gepner model, which is 5 copies of the 3, which is known to correspond to the quintic Calabi-Yau, and I did that by explicit construction. But it's not easy to generalize that, and furthermore it's just one out of the 30,000 cases we need to consider. So I'm sure progress could be made along those lines, but that's not what we're going to do. So here are these boundary coefficients now explicitly, the ones that I mentioned, except that I call them R before also, so that's fine. Now there are lots of details here which I prefer not to explain, and I'm sure you prefer that also. So these are the boundary labels, and there are the degeneracy labels attached to it. These are the Ishibashi labels, also with the degeneracy label. That's all explained here. These are integers, the sizes of discrete groups, but there is a square root, so certainly the whole thing is not an integer. This is a phase. This is a general complex number. So in general, this is indeed a complex number, as I've already announced. So now, how do we go about finding an integral basis? Well, first of all, what we did was we just wrote down these couplings, and in general there is a certain number of boundary states that appears, and there is a certain number of Ishibashi states. Well, first we threw away all the ones that were identical and that were vanishing. That's the obvious thing to do first. And then you have a certain number mu left, which we call the number of axioms in this context. And that number, as I've already said, typically is from tens to a few hundreds. The maximum is 480. The number of boundary states is much larger than the number of axioms by an order of magnitude typically. And now, inspired by the geometric intuition, what we tried to do was find a special basis so that all these boundary coefficients, the imaginary parts basically, can be written in terms of integer coefficients in terms of other boundary coefficients which form a basis. So the idea is here that you select a basis out of all these boundaries, which is indicated by C mu, and if you find the right one, you hope that all these coefficients are integer. Now at this point, this was a big speculation that this was possible. Basically, the generic argument tells you that there should exist an integer basis, but what's the big assumption is that you can write that basis in terms of other boundary states. That was not guaranteed to work. It could just be a random basis oriented in a complicated way, and that would make it extremely hard to find it, presumably. But okay, that was not the case, otherwise I wouldn't be talking about it. So, if you have the previous relation here, then, if these q's are indeed integers, then you've solved the problem. Let me first show that. The instanton multiplicities can be written in terms of these are the annulus coefficients. This is the written index, the number of chiral states in the ground state, the Chen-Patten multiplicity. Now these annulus coefficients can be expressed in terms of these boundary coefficients by this fairly complicated formula. And then if these boundary coefficients, the imaginary parts, can be expanded in terms of integers like this, then what you find is that these integers here are finally expanded in terms of instanton multiplicities of the basic boundary states that you've chosen. So that for a charge xa times ya, you get an expression like this. And let me write that expression again. So if you are able to write all your instanton amplitudes like this, then these are integers because they are themselves instanton multiplicities. And these then determine whether you have a discrete symmetry, because if these numbers are all multiples of an integer n, then clearly the instanton amplitudes themselves must be. So that would then solve the problem. So now let's go back to finding an integer basis. Well, this required some trial and error, and what we basically did was just choose some normalization of these v's, which with the benefit of hindsight was a very bizarre thing to do. You see, these v's are related to the r's, and the r's already have an intrinsic normalization, namely the one that gives you integer annulus coefficients. But because they looked rather horrible, we decided to just randomly normalize one of them to 1 and then see what the rest was. So it was a very strange normalization. When I told my collaborators about this, they almost got a heart attack, but it turned out to be something that worked. With this normalization, simply the first one we tried, it was just luck. It turned out, well, what we did then was compute these dot products here of all these different quantities summed over the number of axioms. It turned out that all of these things, for all 30,000 cases and for all matrices and for all boundaries, came out to be rational numbers at least. And that was already something surprising, because you can easily invent normalizations here where that would not be the case. Now I have to emphasize that we're doing a strange normalization here, but since we're finding a relation between r coefficients and r coefficients, that normalization will drop out in the end. So the normalization is just a trick to find the answer. So now what we're going to do is we choose a set, a randomly chosen set of independent vectors in this space. And that can indeed be done. And now the charges of these boundaries with respect to the basic set would be defined like this. Of course, nothing yet guarantees that these are integers. That's what we want finally. And we can compute these q's by contracting both sides again with the basis, and then you get a relation, a matrix relation, which determines in principle the q's. But these are now rational numbers. So then we can compute these by inverting this matrix, and that already guarantees that at least the charges will be rational. Now, inverting this rational matrix is basically straightforward, but it's not completely easy. Here is a sample of some of the matrix elements that you find in this rational matrix in certain cases. So these are indeed rational numbers. And we have 30,000 matrices like this, and the worst one was 480 by 480. So you don't do this on the back of an envelope. But it can be done. So we still only have rational charges, and that's not quite good enough. So let's now consider one of those boundaries that has indeed a rational charge. So this is one of the boundaries. We expand it in terms of the basis. The rational numbers are of course of the form p over q. And in general indeed they are rational. Now suppose there is a special value of q so that the denominator is 1. Well, then what we do is we throw this guy out of the basis, the one that causes the rational number, and we put this one back in the basis, and you can show that that's always independent, so you can use it as a basis vector. And it's then easy to show that that improves the problem significantly, because then the 1 over q here becomes a q, so that's an integer, and you get here q hat mu over q mu. Now if, for example, these are all half integers, if these are all 2, then also here the 2's drop out. So in other words, in some general sense, the new result is more integral than the previous one. And furthermore, you can show that the volume of the that is spanned by the basis vectors decreases if you do this. It decreases by a factor of q. So the process must converge. It can't go on forever. Now, indeed, in all cases, this converged in a maximum of 19 steps. and in 3 of them it didn't convert to integers. So what happens in those cases is that you have many rational numbers, let's say all half integers for example, and that not a single one of those is 1/2. There are 3 halves, 5 halves, but never 1/2. It seems unlikely, but it happens. In those cases, however, what we could do is start with a different basis and then start again, and luckily it worked then. So finally, we managed to do this for all cases, and this gives a charge lattice for the instanton charges, which we're going to use now. So now we come to examples. So we're going to apply this to our database of models. We have built up in this work a database of about 19,000 chirally distinct models. Chirally distinct means that they're not just different by a few different vector-like states, they're really different chiral states. In the end, chirally it always reduces to the standard model, but since the full group is larger than the standard model, you can have chiral differences in that larger group. So this database contains essentially anything that has ever been discussed in this context, the famous Madrid type models which you've seen many times, SU5 guts, Patti-Salam, trinification, or David Bernstein's model that he talked about on Monday is in there, and there are a few interesting things missing, but not many. And for each class, we've collected up to 10 to the 7 brain configurations. It ranges from 10 to the 7 down to 1 in a few cases. Now what we could have done in those days when we collected this, if we had known about these discrete symmetries, we could already have classified them also according to the discrete symmetries, so that we would have a larger set, because different discrete symmetries really give you a different model, a chirally different model. But that wasn't done. We can only do it a posteriori, and we have now done it for a few of the more interesting ones, namely all Madrid models. Well, basically all models where the Chen-Patton group is U3 times SU2 or SP2 times U1 with only bifundamentals, and a subset of the SU5 models. So we found a Z2 symmetry in about 0.2% of all cases, and a Z3 symmetry in 6% of all cases that we studied. What is still worth mentioning here is that this was before imposing tadpole cancellation. These models still don't have that, so we tried then to also find solutions to the tadpole conditions. That was remarkably successful. It worked in 65% of the cases, whereas I know from experience that in practice it's only 1%. I think this can largely be explained because there was a huge degeneracy in the set, so that once you have one model that satisfies it, then the whole class of 40,000 others also satisfies it. So it's probably a statistical fluke, but okay, it's the way it is. Okay, now, so this is a drawing of these models. This is the Madrid model found in 2000 by Lewis, Marchesano and Rabadan. You have seen it already several times in this conference. This would be an SU5 model. We've looked at cases with 1 extra brain and with 2 extra brains, where the extra brain serves to make the Higgs. Otherwise you can also get the Higgs from here, but that makes it a little bit less plausible. Now here is a full list of all the U3 times SP2 or U2 times U1 models. Here, well, this is some number that we use internally. Here is the entire spectrum. I'm not going to go into detail through this. The only thing I want to show is these are the total numbers in each class. So it goes down to 4 for the least frequent one. This is the number of Z2 symmetries we found in each class, the number of Z3 symmetries, and the number of cases for which the tadpole conditions could be cancelled. And here is this large number, 40,000, which dominates the entire set. Now here is the same thing for the SU5 models, for the U5 models. So we have looked at cases with an extra O1 or an extra U1, or 2 U1s and or U1 and an O1, or 2 U's. And here again are the same multiplicities. So let me show you some explicit examples to show how this works. This is the first one. This is U3 times SP2 times U1 with B minus L, which is broken by axial mixing. This is one of the more desirable models. Okay. Now here are some details about how you get it. That's basically intended for me, so that later I can find it back. I can give you the full spectrum of these models. It looks like this. but that's not really relevant. Only the chiral part is relevant, so I'm not going to ask you to look very long at that. We go back to the basic data of interest here. These are the axion charges for the 3 branes that have U1s. Here they are, and now we can start reading off both the existence of massless U1s and of discrete symmetries. Well, first of all, you can check in all the columns that this relation is satisfied. That means that Y is unbroken. That's very good, otherwise we wouldn't talk about this. Here you can see that this condition is not satisfied. That tells you that B minus L is broken. You can also see that in the first row everything is a multiple of 3. That is something that simply is imposed by us because we multiplied with the Chen pattern multiplicity. And the consequence of that is that color is conserved. That's not a very big deal. The interesting one then is that QA plus QD is 0 mod 2. And that gives you a discrete symmetry which turns out to be just R parity. So we do find R parity in certain cases, but these symmetries, the Z2 symmetries, were only present in 0.2% of the models. So if it's R parity, I don't have to say more, you know how that works. So let's look at the more interesting one. This is the same class, but now these are the action coefficients. This is still the same here, but now you find that there is a combination QB plus, that should have been C plus D, I think, yes, which is 0 mod 3. That tells you that you have a Z3 symmetry. That forbids all the things R parity forbids, and also the QQQL and UUD terms, but unfortunately also neutrino-Majorana mass terms. It allows all Yukawas and it allows also the mu term. So this is not ideal. In the paper by the 4 Spanish that I mentioned earlier, they had a more interesting Z3 symmetry, which unfortunately never came out in our case, but okay, this is at least possible, and the rest would be a matter of statistics. Now this one is very similar, but it has an unbroken B minus L, so that the B minus L already forbids all the dimension 4 operators. But of course then you have to do something about the B minus L. So this doesn't require much further discussion. This one is from a U3 times UT2, so instead of SP2 we have a U2 here, and it has an unbroken B minus L. So it's very similar to the previous one, but now it also forbids the QQQL and UUD terms. Now we have 13 examples in our paper, so let me just jump directly to example 13. I'm not going to show them all. This case is rather different from all the others. This is an SU5 model, so now the first row is a multiple of 5, which is SU5 pentality, which of course comes out. And you find that the sum of all the charges is 0 mod 2, which means that you have a kind of funny matter parity. Any strings that stretch between the matter branes have charge 0. Strings that, if you add a hidden sector, then strings that stretch between the matter sector and the hidden sector have parity 1. And if they in addition have 0 charge, which in principle is possible in these models, they would be perhaps suitable as dark matter without having, well, this model has supersymmetry, but if you realize this without supersymmetry, you would have a kind of matter parity very similar to R parity in the MSSM. So that's possible. I'm not going to say that that's the solution to the dark matter problem, but it's just interesting to note. So that brings me to my conclusions. We know how to determine discrete symmetries in Gepner orientifolds, and that was the main goal. Now I've also tried to tell you that clearly there is room for improvement. If you have to work your way through all these horrible rational matrices and at the end find a simple answer, you kind of hope that a year from now you can give a talk saying, well, it trivially follows from this and this, but we're not there yet. If anybody has an idea about that, I would like to hear it. And of course I would also like to know how its principle works without explicit computation in more generic CFTs. Now we can find many of the known examples in field theory indeed back in this class, and discrete symmetries do not seem to be very common in this particular class. So the interesting thing is they were rather common in toric toroidal orientifolds, as Lewis and collaborators have shown. They become less common here, and it seems to suggest that perhaps in the general landscape they would be even less common, but I cannot make very strong statements about that. What is interesting is that they occur more than you would expect based on the random numbers. That is, if you take these axion charges and you just assume that they are random numbers, we find more discrete symmetries than you would expect. Another remark is that there is a positive correlation, presumably, between tadpole cancellation, the masslessness of the Y, and the presence of discrete symmetries. We kind of see that experimentally, and you can also expect that because all of these three conditions are favored if you have a small number of H21. You have fewer tadpole conditions, fewer axions, so these three kind of go together. So you can, this positive correlation would be a positive thing if you want to satisfy all of these things simultaneously. So on that positive note, I'd like to end. Thank you.
Thank you very much.
So could it be that there is sort of a Verlinde type of formula at work for getting these integer numbers eventually? That's the taste of it, right? So you had
a Verlinde type formula. Now let me see which Verlinde, which Verlinde first of all, which formula. You mean the
fusion coefficients in terms of the S matrix, where you also have.
Yeah, but there is a Verlinde-like formula in the basis of this. The axion, the annulus coefficients are integers because of a Verlinde-like formula. That goes back to the work of Cardy in '89. Who used that, and you know it.
Yeah, but you're getting linear combinations. You're trying to make everything that eventually you get integers out of some complex numbers. I think the same problem happens if you just look at the tadpole cancellation equations, which are the same. Also there the coefficients are complex numbers, at least for the cases we were looking at. You can find linear combinations also there, that you can write them as a linear combination of just the integer coefficients.
Yes, I should say one more thing about that. For the tadpole conditions, we don't just need A minus RAC, but also the sum. So I've tried this analysis also for the sum of the coefficients, and there it doesn't really work so well. There we don't have an integer basis yet. But when we do tadpole cancellation in these models, usually we write down the coefficients in complex form, and then reduce it, and usually it indeed reduces to integers. But it's not yet fully understood, at least not by me, how that really works fundamentally. But I think basically, yes, you're right. It still has to be.
There's a miracle going on. There's a miracle going on.
Yeah, there's definitely a miracle going on, and miracles are things we want to understand. So yes, I agree with that.
Okay. If there's no further questions, thank you very much again.